Hi everyone! In this video we're going to start learning about rational functions and their graphs. Rational function is a function that has a form of a fraction where both the numerator and the denominator are polynomials. And of course a polynomial in the denominator cannot be equal to 0. Graphs of rational functions have different and interesting shapes. Here's the first two examples. First we'll observe the functions. Notice how it has a form of a fraction with polynomial on the top and on the bottom. In this case, in the numerator, we have a constant polynomial. And here's another function. The polynomial of degree 2 in the numerator and the polynomial of degree 4 in the denominator. These are the corresponding graphs. Besides interesting shapes that graphs of rational functions take, many of these graphs have one similar feature. The end behavior of these graphs is such that they approach a specific line that they will never cross or touch. For example, this line here at x equals 3. This end of the graph approaches this line, and this end of this graph approaches this line, but from the different side. Well, the ends of the graph will not cross or touch this vertical line. There's actually another line like that for this graph. This horizontal line, that's actually the x-axis. Again, this end of this graph, this right end of this graph, and this left end are approaching the x-axis, but they will never cross or touch it. Can you think of a line like that for the graph on the right? It's actually also the x-axis. Both the right and the left ends approach the x-axis. These kind of lines that the ends of the graph approach but never cross or touch are called the asymptotes of the graph. Here's the definition. Let's look at two more graphs of rational functions and visually try to guess where the asymptotes those graphs might be. Okay, here we have two more rational functions and their graphs. Where do you think the asymptote for this graph? It's this horizontal line that crosses the y-axis at 4. So in other words, it's the line y equals 4. Notice how the right end of the graph approaches this line from above and the left end of the graph approaches this line from below. How about this graph? Can you think where it has its asymptotes? One of the asymptotes is the vertical line at x equals 1, and it also has a slant asymptote. So asymptotes don't have to be vertical or horizontal lines only. They can also be slant, or we'll also say oblique lines. Asymptotes play an important role, especially when we try to graph a rational function. In fact, determining asymptotes of a graph is one of the first things we do, because asymptotes really help us to understand the behavior of a graph. So let's learn how to find asymptotes. Here I'm reminding myself and everyone the form of a rational function, and I'm also showing the expanded numerator and the denominator. Remember, they're polynomials. Here we can see the leading terms, and an m represent degrees of those polynomials. Remember, that's the same as the highest power of x. A sub n and b sub m are the leading coefficients, and a sub 0 and b sub 0 are the constant terms. I'm going to refer to these expanded forms when I show you how to find the asymptotes. Let's start with a vertical asymptote. It occurs at values of x where q of x equals 0. Q of x is the polynomial in the denominator of a rational function, and all values of x that make it 0 will be the places where the graph has its vertical asymptotes. And of course, to find those values of x, we just have to solve this polynomial equation. Let's go back to the four graphs that we already saw and revisit the vertical asymptotes. Here's our first graph, and it has its vertical asymptote at x equals 3. Well, look at the function itself. See how 3 makes the denominator equal 0? Now the second graph doesn't have any vertical asymptotes. Well, let's look at its denominator. Can this denominator be ever equal 0? No. X to the 4th power will always be something positive, well, or 0, if we plug in 0 for x, but then we add 1. So it means that no matter what we plug in for x in the denominator, the result is always 1 or greater. In other words, this denominator can never be equal to 0. And as a result, the graph of this function doesn't have any vertical asymptotes. These are the other two graphs. Third one doesn't have any vertical asymptotes as well. And exactly for the same reason, look at the denominator. It's 2x squared plus 1. So this denominator can never be equal to 0. And the last graph does have a vertical asymptote at x equals 1. because x equals 1 makes the denominator equal 0. Now let's talk about horizontal asymptotes. To know whether a graph has a horizontal asymptote or not, and what kind of horizontal asymptote, we need to go over 3 different cases. Here they are. These 3 cases show how n and m can be compared to each other. And if we look at the expanded form of this general rational function, we'll see that n and m represent the highest powers of x in both polynomials, in other words, degrees of those polynomials. And we're going to be comparing the degree of the numerator with the degree of the denominator in this order. So if n is less than m, then the graph will have a horizontal asymptote, and that's going to be the x-axis. That's the same as the line with the equation y equals 0. Now, if the degrees of the polynomials from the numerator and denominator are the same, n equals m, then the corresponding graph will also have a horizontal asymptote, and it's going to be a line defined by the following equation, y equals a sub n over b sub m. Well, if we look at the expanded form of our general rational function, we'll see that these are the leading coefficients. And here's the last case, when n is greater than m. In other words, the degree of the top polynomial is greater than the degree of the bottom polynomial. In this case, the graph will not have any horizontal asymptotes. Let's check these cases with our 4 graphs. Our first graph does have a horizontal asymptote. It's this line. So let's look at the degrees of the polynomials in the numerator and the denominator. The polynomial in the numerator is the constant polynomial, so its degree is 0, and the degree of the polynomial in the denominator is 1, which means that we're looking at this case, n is less than m. Top degree is less than the bottom degree, and in this case, the horizontal asymptote is the x-axis. Well, we can see it on the graph. Let's look at the second graph. It also has the horizontal asymptote. Degree of the numerator is 2, degree of the denominator is 4, and this makes the same case. N is less than m, so the horizontal asymptote is the x-axis. For function number 3, the degrees of the polynomials in the numerator and denominator are the same. It's degree 2. When degrees are the same, the asymptote is a horizontal line that has this equation y equals a sub n over b sub m. Remember, these are the leading coefficients from the numerator and the denominator. So in our case, the leading coefficients are 8 and 2. So this horizontal asymptote has equation y equals, well, 8 over 2, which is the same as 4. Y equals 4. And that's exactly the line shown in this picture. See how it crosses the y-axis at 4. And let's look at this last function. The degree of the polynomial in the numerator is 2. The degree of the polynomial in the denominator is 1, which means that the top degree is greater than the bottom one, or n is greater than m. Well, in this case, graph does not have any horizontal asymptotes, and we can see that on the picture, no horizontal asymptotes. And finally, let's talk about oblique or slant asymptotes. This type of asymptote occurs if the degree of the polynomial in the numerator, p of x, is exactly 1 more than the degree of the polynomial in the denominator, q of x. Then to find that asymptote, to find its equation, I should say, we need to divide p of x by q of x. In other words, the polynomial in the numerator has to be divided by the polynomial in the denominator. We can either use synthetic division if it's applicable, or the long division for that. And since degrees differ by just 1, the result of the division, another polynomial of degree 1, in other words, a linear function. And that function will be the same as the equation of the oblique or slant asymptote. After all, it's a straight line, so it has to be a linear equation, right? It's going to have this form, y equals mx plus b. Hopefully you recognize this as an equation of a line. Let's check oblique asymptotes in our 4 examples. The first 2 don't have any oblique asymptotes. Why is that? Well, because for each, the degree of the numerator is not exactly 1 more than degree of the denominator. Graph 3 doesn't have an oblique asymptote as well, and that's because the degree of the numerator is exactly the same as the degree of the denominator. It's not 1 more. However, graph number 4 does have an oblique or slant asymptote. Here's that line. And as you can see, in this case, the degree of the numerator, which is 2, is exactly 1 more than the degree of the denominator, which is 1. Let me demonstrate the steps that we would have to take if we had to find and graph this slant asymptote. For that, we would have to divide the polynomial in the numerator, x squared plus 1, by the polynomial in the denominator, which is x minus 1. Since we're dividing by this simple linear equation x minus a number, we can perform synthetic division. However, first I need to realize that not all powers of x are represented here. It's missing x to the first power. So I'm going to rewrite it as x squared plus 0 times x plus 1. Next, I write down those coefficients on the line. 1, 0, 1. Constant that's opposite to the one I see in the second expression, I place in the box here. So it's 1. And then I start the steps. 1 goes down. 1 times 1 is 1. I place it here. 0 plus 1 is 1. And I repeat the cycle. 1 times 1 is 1. I place it here. And add 1 plus 1 is 2. Remember, the last digit that we get is the remainder. And all numbers that come before the remainder are the coefficients in the resulting polynomial. So this is how we would officially have to write the answer for this division. 1x, 1 comes from this number here, plus 1, that's this one here, plus 2, which is the remainder, over x minus 1. X minus 1 is the expression by which we divided. So that's the way we write down the answer, but the only part that we're interested in, remember we're trying to find equation of the oblique asymptote, is this part here. That's how I write it down. Y equals, instead of 1x, I just wrote x plus 1. And we can see that that's exactly this line. This 1 represents the y-intercept of that line. See how it crosses the y-axis at 1. And the slope is 1, or 1 over 1. 1 up, 1 over, 1 up, 1 over, and so on. So slant asymptotes require a little bit more work when you have to find them, and these are the steps. In the next video, we'll do more examples where we have to find asymptote of a rational function.